can't even see my screen. So how do I know you guys can see it? Can anyone see my screen? Just great. Okay. Let me cross check if my tabs also active. Yeah, great. Okay. So something Oluwatobi is saying to learn for someone that has vast experience. And I don't have I'm not Yan Lekum, so I don't have vast experience. Okay, someone is saying to know more on data science. Well, it might be a little bit disappointed. And someone is saying to connect with everyone. Oh well. So today's session is going to be like this. I'm going to make a few assumptions. I'm assuming that even if you're not good with Python, but you've probably seen a line of Python code before. And if you haven't, that's also fine. But I hope you catch up fast enough. And about data science, I'm not going to go into the in-depth of data science. Unfortunately, it's machine learning, and I'm going to be focused on that. And so when we are inside of coding, right, I'm going to skip a lot of usual data science things, right, and go straight to the machine learning because that's like the focus of today. So Python for machine learning, someone is thinking, are we teaching Python or are we teaching machine learning? It just means teaching machine learning using Python. And Python isn't the only language, right? You have JAX, you have I don't think they use R. I think you have like other languages that you can use for machine learning. So maybe in another session, I'm going to show you guys how to write with JAX. JAX is like more efficient, faster, blah, blah, blah. And it looks like Python a bit. So yeah, but let's start with this, okay? So today, when I was compiling this session, I realized that 1 hour is definitely not going to be enough. There is so much to say. There's so much to talk about. And I should have updated this agenda, but basically, we just talk about why Python, TensorFlow, Python. We're not going to really go in depth to matrices because matrices involve that we do a lot of writing, sketch stuff. And that would take a lot of time. So I'm skipping that. Just going to mention it briefly. We're also going to talk about linear models for regression and linear models for classification. So I thought of doing decision trees, but I'm sure by that time it'll probably be 7 p.m. because we're going in depth, right? We're not just build model. You're going to know how the model works, why the model does what it does. So yeah, it's going to be really comprehensive. But I think what I'm going to do is I'm going to have a follow-up session with this so that we go above this, right? And then we actually know what decision trees are. And there's so much to machine learning beyond just linear models, right? But today our main focus is going to be on linear models. So I don't have so many slides. I think it's and one other are just like all my slides. So why Python? Python, multi-versatile, uh, Django, these Django is for like APIs, all kind of stuff. So many things you can use Python for. Python also for data science. Then why Python for machine learning? Well, I think you should probably ask the godfathers of Python why they decide to use Python for machine learning, but then it has proven to be easy, right? Easy to abstract code in terms of abstraction and all those kind of things because machine learning has a lot of right. And again, it's really easy to like load data, visualize statistics, and all those other cool stuff you want to do. And although many people usually use Jupyter notebooks, well, we're going to be using Colab because I don't want us to go through the hassle of installing Jupyter notebooks, installing Anaconda, installing Python, and someone's like, oh, this doesn't run on your laptop or your Windows or something. Especially Windows users, no offense, but there are like tons of issues you run into when you're trying to set these things up, and this is probably not the best platform to get started with that. So yeah. Then sorry. Then this is supposed to be like the next code, but I want to quickly go over the resources I shared in the email for those that probably didn't find it. So let me send it again in the chat. So Yeah, please check the chat. I sent like 3 links. Right, the first is supposed to introduce you to what machine learning is for those who don't know anything about machine learning, and the second is supposed to go a bit further, right? And the third is supposed to teach you about Python, just like to freshen you up. I know it like I kind of said it a bit late, but let's quickly do that. So machine learning for those who don't know anything about machine learning. So this is a Microsoft Learn. Yeah, I wrote the article and published on Microsoft Learn, so you can always like check it out. Um, and basically, what is machine learning? So machine learning is not AI, first of all. No. Um, Machine learning is not AI. AI is like it's very debatable. Some people say it's like an umbrella term, some people say it's under machine learning, some people say all sorts of things. But I would say that machine learning is under AI. It's sort of a field in AI, right? That specifically focuses on developing algorithms and statistical models. So notice I said algorithms when I said statistical models because you're going to be needing these two things. I know you probably don't like statistics, but I promise not to scare you. That's why when people say having a background in statistics or calculus, all those things is really important. It is useful, especially if you're looking to build a career in it. So if you're just looking to like just get job or just do stuff, not really building a career, then maybe not. But if you're looking to actually building a career in this, then I would advise you actually but again, what I mean is that I don't mean you have to have a PhD or BSc. No, no, no. What I just mean is your high school mathematics is probably just good enough for you to start. Okay. And machine learning itself has like its own subfields. You have supervised learning, you have unsupervised learning, and you have reinforcement learning. So by machine learning, it means you're trying to like teach the computer how to act. Let me not say act on its own. So I'm not giving you the intent of creating a Jarvis, but what I'm trying to say is teaching the computer how to be intelligent, right? Or I would argue mimic intelligence. Okay, so by supervised learning, it's the concept of like having a supervisor, right? A lecturer or a teacher that teaches you, then gives you exam to do, right? So it gives you exam based on what you taught in class. We're not talking about those lecturers that never teach and then you see whatever in your exam, right? We're talking about teaching and actually giving you an exam similar to what you've been taught. So that's like the whole idea behind supervised learning, right? Supervised. And unsupervised is those lecturers that you don't see them through the semester, you only see them on exam day as invigilators and you dare not talk, right? So that's like unsupervised learning. You do not provide the model with anything, any idea or example of what it should do, what it does. You just give it to him and then expect him to just guess and figure things out, right? And that's what unsupervised learning is. Then reinforcement learning, which is currently like my best field right now, uh is a little bit complex than before in the sense that the goal is totally different, right? The goal is more like you're sending the model into the world to have adventure, explore, and if you make certain decisions, you get penalized. If you make certain decisions, you get rewarded. Really, it's more like an adventure game kind of stuff. So reinforcement learning is actually being used in games, right? Games, especially games where you have like this AI assistant that they're like really smart. Yeah, some of them use reinforcement learning. So there are other types like deep learning, transfer learning, Gen AI. Yeah, like those cool stuff if everyone wants to do. But don't worry, we're not going to do that in this session. It's way more complex or beyond this class. Um, so how machine learning works? Yeah, I'm trying to zoom this in so everyone can see. So the whole life cycle starts with a problem, right? So like any other software engineering task, you have a problem you want to solve, you have an outcome, right? And then just that the process is a little different. So in software, you have software development life cycle. In machine learning, you have machine learning life cycle, or we call it MLOps, right? And starts with, okay, you have the problem, the business leaders, they decide, okay, this is what we want to do, this is how we want to, this is the results we want to get, right? These are the things we have. And data scientist comes and say, okay, maybe the first one to do is get the data. And the question is from where, right? Do we already have like scattered databases everywhere? Or do we already have like something we can use? Or we have to go into the world and actually search for, like when you see the acts or surveys, yeah, there is need to collect data, right? And then after that, you clean it, you pre-process it, because when it comes, it's usually like very rough and wild kind of stuff. And the next thing you want to do is understand how the data, like understand the data, understand what is missing, what you need to add, kind of stuff. And then build a model. So decide which model you want to use, select the model, train, right? Test, test the model, check, and by testing, not just how accurate it is, but also seeing if it aligns with the business KPIs, key performance index, and then um, select if it's relevant, you deploy it, and then people start using it, right? So I mean, this differs from case to case. From OpenAI, it looks different, but it's really literally like the underlying thing. Okay, so I mean, you can literally go through this article on your own to read about it. So there are various like data collection methods. Sorry, somebody keeps pinging me. Okay, great. I thought that I had. Wait, can everyone still hear me? Just want to be sure. Okay, so okay, great. So yeah, where did I stop? So data collection, just like I explained, and there's so many reward machine learning use cases. I'm probably thinking ChatGPT, yes, ChatGPT one, your phone, Siri, Google Assistant, Amazon telling you customers also bought, Netflix, chatbots. Chatbots are quite okay, yeah, chatbot. Advertisement, the ads you get actually use machine learning. Um, Weather forecasting, right? Is it going to rain today? How much rain? Is it going to be sunny tomorrow? And maybe just for your consumption, some misconceptions is that you can use machine learning to do anything. No, you cannot. You need to be very good in mathematics and statistics. No, also you probably need to have like high school background if you're looking to get a career. But if you're looking to just use it, you don't really need all that. Yeah, you don't really need to. Yeah, you really don't, because the barrier has like really been brought down. I remember when I started learning, we did a lot of maths, but now it's like a lot easier for you. And also people saying, oh, it's machine learning, it's supposed to give you accurate results. That's a lie. Even ChatGPT hallucinates. So who ChatGPT is hallucinating? Who is machine learning? Anyways, uh, people also think that machine learning is something that is it should be able to make decisions on its own. You should be able to think, I mean, this is the right thing, it's supposed to know it. It cannot know it. It's not alive. It's just a set of algorithms, right? Making decisions based on patterns that they've seen. Right. So then on the second article, this one goes like a little bit deeper and basically talks about the kind of supervised learning. So supervised learning, like I mentioned, is when you have like you teach the model, you show the model samples of your data, and then you give it like a new data it has not seen and ask it to predict a particular target, right? So a good example of this is I don't want to use cat and dogs, but let me say different kind of Ankara, right? And then you say, oh, this Ankara is from Nigeria, this Ankara is from Ghana, this Ankara is from Senegal, this Ankara is from this place. And then you show it a different Ankara from maybe another country in the East that it has never seen before. You're like, okay, or maybe a different Ankara, but it's from Nigeria, but it has never seen that Ankara before. You're like, okay, which country do you think this Ankara is from? Then so that's like supervised learning. So you've shown it samples before, and then you give it like something it does not see and ask it to predict, knowing that what you're asking it to predict is within what you've taught it. So if by chance it sees something that it has not seen before and not in probably the list of classes you provided before, probably should just say unknown, right? I mean, you can always do that to test it. And so under this kind of learning, we have classification, avoidance, we have regression. Classification is just like the one I've given you where, saying, is it Ankara from Nigeria or Senegal or this? But then regression is when, instead of having classes, you have like continuous variables. For example, right, you're trying to predict somebody's body mass index, like we would see. And So you say, okay, this is the height and the weight of this person. This is the BMI. Height, weight, this is the BMI. So there is a new patient that just got into the hospital, predicts the BMI of the person. Yeah. So that value is not a class. It is a continuous value. I mean, it can be 19 for somebody, it can be 25 for another person, it can be like range of values, right? And that's why it's regression. Okay. If you have questions, you can just like either drop it in the chat or raise your hand at any time so I can like answer. Because I'm not sure I might be able to take questions at the end. So it's better if I just answer it now. Okay. And if I'm too fast, also let me know. Okay. So we have like semi-supervised learning. In semi-supervised learning, it's like half half supervised, half unsupervised. But what it basically means is you give it data, right? Large amount of data um that hasn't been classified, right? Or does not have a target. And then you now give it a smaller set of data um that has been classified. So for example, its classification, you give it a very small sample of um maybe of maybe you give it fruits. This picture of orange, this is an orange. Picture of mango, this is mango, this like that. Maybe you give it like 10 and give it 100 of unlabeled pictures, right? So it's sort of a mix. And then we usually use it. A very good use case of this is during data annotation, where like you want to label so many data, and if a human is going to do that, it's going to take the person months to do, right? So yeah, that's somewhere where semi-supervised learning is very useful. We also have unsupervised. Unsupervised is where, like I said, you just give it find patterns in this data. And we have like so many algorithms on that. We have clustering, where it tries to find groups. Like it just tries to group the data. Oh, this data looks similar. Let's group them together. It has association rules, right? Which tries to find relations between the data, right? Um, and they also have like dimensionality reduction, which tries to it also tries to do what clustering does, but then reduce it to a set of what I call or what we call principal variables, right? So the funny thing is this kind of unsupervised learning is usually used during one of the steps in data science, right? Especially where we have like very large data set and we're trying to find which features exactly matter, because you might have very large data set, but you don't know which one is useful, which one is not. So this is also a very good case. I don't want to talk too much about deep learning, but deep learning, you have computer vision, NLP, you have GenAI, and also reinforcement learning sort of falls into deep learning because there's now deep reinforcement learning. Initially, the reinforcement learning is not under deep learning, but now you have deep reinforcement learning. So, okay. And you can, of course, you can always like go and read the stuff on your own in the chat. Okay. Great. So now let's quickly brush through Python and some basic Python codes. Again, if you feel I'm too fast, please stop me, right, or ask questions so that I can calm down. So this is like a simple Python code. You can perform like simple arithmetic like 3 plus 4, 10 minus 4, 10 divided by 2, 11 divided by 2, 11 modulo 2. This divided by is what we call integer division, right? And what it does is instead of returning the, we can say fractional part, it just like discards the fractional part with it. Okay. And in Python, Python sort of follows rule of BODMAS, but I think it's called BODMAS. I think there's a P. Regardless, what it just follows is the order of precedence. So whether it's PODMAS or BODMAS or whatever mass, right? It means there's a precedence of operations. Parentheses is first, then there is, I think we call that bitwise operations. Bitwise operation next, then you have multiplication, addition, things. You can run through this yourself, right? So I just want to like just go over, and then you can do all sort of math uh math functions like sine. You can take the sine, you can take the log, the square root, the absolute, right? You can take the floor. Floor is just like reducing it to the nearest whole number. Round round down to the nearest whole number. Round to the nearest decimal place. Cell is just like round up. Is what floor does, but rounding up. That is, it adds one to the next one. Okay, and you can run a for loop if you have like a list of things and you want to run over them. You can use Python's for loop, right? The range here, what the range allows us to sorry. Sorry. What the range allows us to do is it lists numbers from zero by default, from zero to the last number to the number you provide. So if I provide 5 here, list numbers from 0 to 5. If I say range from 1,5, list numbers from, no, sorry, 0 to 4. Python does not include the last number. So 5 years going to list 0 to 4, that's 5 digits. If I say 1,5, it's going to list start from 1 and end at 4. Yeah. So you can also like loop through lists using enumerate. There's a mapping function, zip function to combine like two tuples, two lists, or whatever. Sorry. Um, okay, so in Python, there are also like various data types. You have a Boolean, integer, float, string, null, or none. That is maybe if for any instance you just want to keep it empty, maybe you want to keep it empty for now, but fill it with something later, right? Yeah, those are like I would call them the primary data types. If you're familiar with data structures, you probably know that they are abstract data types. So tuple, set, list, so some of the abstract data types. So tuples are immutable. That is, whatever you add in the tuple stays there. You cannot remove or add. It's just there. So it is very good, especially where you want to have like let me give you a good case is maybe you want to have a field that doesn't change. So if this is the value, it remains the value to God knows when. You can't add, you can't do anything to that, right? And then you can do all sort of operations on tuples like slicing. Slicing is when you take like a list or like a loaf of bread and just cut a part. So you cut a part doesn't mean it comes out of the original list changes. The original list is just there. You're just taking that part. Like it's like eating your cake and having it, right? So you take a slice of the cake, but the original cake remains, but then you still have the slice. Yeah. So that's like what slicing does in tuples. Okay. Then there is sets, like similar to the same set we know in high school, where it's like set of ordered numbers. Sorry, set of non-duplicate numbers, right? So in sets, you cannot have duplicates. It always have like, so it's very good if you need to like make sure a list, maybe you have a list and then you want to remove duplicates. Sets are like good for that. You can, yeah. So you can also perform things like intersection, union, all those charts we used to draw in school. Yeah, you can do that here also. Another thing is lists. So lists are like very common. You see them everywhere. You can add, remove. You can have lists of various data types. So the ones I mentioned before, you probably have like single data types, but I think you can actually have multiple. So in lists, you can have like list of numbers, letters, all sort of things together, right? And you can select a number, select a list, do all kind of stuff, append, remove, extend, insert, delete, all kind of operations on list, reverse also. Okay. Um, then in Python, we also have conditional statement. That is, if something is greater than something, do something. And then we have elif. So elif is just like if and else combined together, right? Yeah, very, very cool. Saves me the if else Yeah. So if and else, so that's elif, right? So else, if number is equal to 3, else, that's the final else, then do whatever you want to do. And we can also have like conditional statements inside of loops, right? So you're looking through a list, but then if you reach a certain point, stop the list or do whatever. Okay. And another loop, I think I mentioned earlier, is while loop. So you have while, you have for. In I think in C, or is it C sharp or one of the C's, you have do while. So you don't have do while here, just have while. Okay. And let me see. Oof. In Python, you have files, functions, classes, inheritance. So this part is a little bit more technical, but basically what you're doing here is how to load files, how to load directory, navigate through directory, all those things. Python is very good for automation, where and also how to define a function. Functions are usually defined using DEF. Yeah. So your function can decide to return a value or not. Yeah, so these are like all kind of functions. And this is Python typing. So Python typing help us to how do I put it? Make sure that we pass in the right parameters and we pass out the right variables. It's like strict. I'm trying to find if strict typing is the strict. There is a particular word we usually use for it. Forgotten, but it's just like strict definition. So if something is to be an integer, it can only be an integer. If it's not an integer, it's going to give an error, right? So really good, especially when you have like critical applications. But really, it's just good programming uh programming experience. Okay, and classes. So classes, fortunately, I didn't use any of that because I felt maybe it's gonna be a little complex. That is for like today's main class. But a class allows you to, like, in a class you can have so many functions, right? And each function has its own. It's more like creating like an abstraction. So it just makes code easy for you to understand, read. And the cool thing about classes is that it helps you pass data easily. So for example, you define a function somewhere, right? So instead of having to call the function multiple, you can just call it once, and that data is stored in the memory, and you can use it anywhere else without having to define the function again. So cool, really cool stuff. Um, you can learn about that. And there are other examples like polymorphism. I think it's endomorphism. I think I'm trying to miss the morphisms now. But yeah, it's something you can just like run and read up on your own. This is supposed to introduce pandas and numpy, but uh we don't assume. Okay, yeah. Basically this is like Python. It's Python, yeah, but these are just libraries that help you do some of the things mentioned before in more efficient ways. For example, creating arrays. You can create an array in Python, right? Using lists or whatever you want to use. But you can also create the same thing in NumPy, right? NumPy it's does not have a full meaning. But what it does, it's like a um I won't say numerical library, but helps you do all those numerical stuff. Yeah. To calculate the median, mode, standard deviation. It also does that thing that Python does, where it generates like a list of numbers from a particular range, helps you reshape, all kind of stuff. So Pandas has series and data frame. Series is like in series you have like a one-dimensional data set, right, that you want to perform operations on. Let me see. Okay, I don't want to run this right now. Okay, let me quickly do this so I can show you what it looks like. That was not time. Just trying to connect. Okay, I have to. No, I have to. I have to define NumPy. Import NumPy. Okay. Aha. So this is what a series looks like. It's just like one column or one feature, right? Yeah. So a data frame is like data set. So it has like so many other features, and that's what we're going to be working with mostly in today's class. All right. Yeah. So that's like the basics of what you need to know. You can like run this later on your own. And move to so yeah, I mentioned I'm gonna talk about TensorFlow. So TensorFlow is pretty cool. Yeah. One in Windows users might have I run into one or two problems by installing this. So I'd advise that you install versions greater than 2.0 and you install them in a virtual environment. Very important, especially if you've not done any of this before, you're safe. But if you've tried to like maybe write Python before or try to do some data science, you might actually like just destroy your environment. So just do this in a new environment, speaking from experience. So TensorFlow helps you do more machine learning. It's like a library, yeah, but then it has much more complex functions than pandas and NumPy. So it's built specifically for machine learning, right? So it has its own efficient way of loading data sets, building models. Like this is an example, right? So build a simple neural network, compile the model, fit, and you evaluate. So that's like a very small quick start of what like a simple neural network looks like with TensorFlow. Sorry, but PyTorch has like its own version, similar but not exactly the same code. Let me see. Uh, so this is PyTorch. You can choose. You can. I know both, so it's good to know both. Yeah. But you have more people are beginning to write more in PyTorch than TensorFlow. Yeah, I don't know why, but it's good to know both. So PyTorch also does like it's also for machine learning and deep learning, right? And let me see if I can find some quick start code somewhere. Uh, hmm, so PyTorch is more. I think my biased perspective though about PyTorch is that it's easily readable than TensorFlow. I mean, you don't have so many strange stuff. Maybe just a thing with Google generally. They just enjoy making life difficult. My own perspective again. Okay. Yeah. So okay, yeah, why that loads? If we're going to today's session, it's time is almost up, right? But um like I said, I brushed through Python, brushed through data science, just so that everyone is up to date. Um, we're going to specifically be doing linear models for regression and classification. There is so much in machine learning, but because I specifically choose to go in depth, might not have so much time again. Okay. So I already helped like write all the libraries you need to install already, so you don't need to like stress over it. This is like a helper function to download like data set from my own Google Drive. And sorry if you feel scared, my apologies. I know you're like saying, oh, what is this? Don't worry, it's not all that scary. I intentionally did not want to make it too much math. But I think that this is just good. Like just know it so that you see it tomorrow somewhere and you're not afraid. So linear regression or linear models generally, what they typically do is when you have like wait, let me for my tab, my switch my screen soon, depending on yeah, as needs, right? Depend yeah. So linear models, you have like let's say you have like n observations. Your n observations just like numbers from 1 to n, right? And you have corresponding targets. Remember when I was explaining supervised learning, I said that you have like the data, you have the targets, or you have the classes, right? So the data is like your number of observation, the classes is like your targets, right? Okay, and now your goal is to predict a new target given a new data set, a new value of X, where your X is your observation. Okay, now I'm giving the idea of having just like one, for example, like a panda series, right? One. But in real life, of course, you have many, right? But this is just like to give you a picture. Okay, and now a simple linear regression for this is y equals to mx plus c. Oh, you've probably done this before in your, again, high school, right? Drawing all those quadratic graphs and all those things that if your graph is not neat, you're probably getting a -10 or something. Okay, so now it's that's like an example of a linear model, like the very basic one. So, and in linear models, right, the C there, right, is what we call the bias. So not bias like statistical bias, so like it's called the bias, and I'll explain more, right? And you can write, so for example, you're given you have 5 features, and I'm calling those features x1, x2, x3, x4, right? So you have four of these features. If I'm going to write a linear model for that, so that's going to be my y, right, of x, such that I have the bias plus the linear combination of all these features, right? Good. Now, I'm sure like, what's the W? So the W and the X are what we call parameters. Okay, so it's linear because not because it's on a straight line, but because you can have like a simple or a straightforward equation to represent it. Okay, now so this is a simple example. So for example, you have a data set of 2 features, right? 2 features is called like a 2-dimensional array. If you have 3 features, you have 3-dimensional array. If you have 4 features, you have 4-dimensional array. Okay, so this is a 2-dimensional array, and what I call this is so I said let it be a data set represented as matrix of n-dimensional vectors where the dimension is equivalent to the number of features. Okay, so suppose we have this matrix now, and we have the corresponding target. So now we get a new matrix here. And now we're saying, okay, this feature here is the weight, this feature here is the height. And the problem is you have the weight, you have the height, calculate or predict what the body mass. I know this can be done like simple, but I'm just giving this as an illustration for this class, right? And this target here is the body mass index, BMI. Okay, so now this is like sample of what we already have, and this is like yeah, sample of what we already have. But now we have like new weight, we have a new height. What is going to be the BMI for this new weight and new height, right? So that's a problem that we can solve using linear regression. And let me see what time is. Okay, so sorry again, I'm rushing through it because like we're literally out of time. But if you have a question, please like raise your hand. Okay. Yeah, so we import the libraries, pandas, numpy, matplotlib, and seaborn. So matplotlib and seaborn is for visualization. And this one I'm just doing here is just like to set parameters so that I don't have to define it every single time. I can just define, like, for example, I want to plot a graph, I can just define the size of that graph at once. So I don't have to define every single time. Yeah. Okay. Yeah, so import the library, download the data set. So if you run this function, this has already been defined earlier in the helper function. Okay, so you just run the function and download data set to your environment here, right? So I specifically, like, interesting, I found a data set that actually has like You have the height, you have the weight, and you have the BMI. I mean, I thought that was just for like illustration, but I did find one. So we're gonna use that one. And we have like 1,000, 10,000 rows, right? So 10,000 rows, and you have like three three columns or three features. The first is the height, the second is the weight, the third is the BMI. But what we want to predict here is that BMI. Okay. So now if we let's just see what the data set actually looks like. So this is what the weight looks like. So if I'm supposed to draw like a regression line on the more like the line of best fits for this data set, seems to be somewhere around the middle, right? Seems to be somewhere around the middle for the weight, and this is for the height, right? Now, I did jump a lot of data science things here. For example, um, checking the df.describe, which basically gives like a summary statistics of what the data set looks like. You can see the mean, right, the weight. And one of the importance of checking these things is that you can see if your data set is skewed maybe towards particular values, or if it has like outliers, or yeah, or if it has missing values or kind of stuff. Okay. But I'm going to be assuming that our data set is just perfect and it's just fine, right? And I can confirm if it has missing values here. So if it has missing values, it's not supposed to be equal to, I'm saying 10,000 non-null, which means 10,000 not empty. Yeah. So, and everything has like 10,000 too. There are no missing. If there are missing values, you have like a lesser number. Okay. And you can plot a heat map for that. Shows that there are no missing values. Okay. So we tried something really interesting here. And try to build like a linear model from scratch using Python code. Okay. So the first thing I want to do is usually in machine learning, right? Assuming the data set we're given, like we have like 10,000, we have all the all the targets and all the so the idea is this: if we build a model, how can we test or know how accurate it is? We need to build and then test, right? So it's just like a lecturer that comes to the exam. He already has his marking guide. Yeah, so it gives you the question and then cross checks his own marking guide. So that's what we're going to do, right? So we're going to give it the question. So the question, maybe we're going to say it's like 80% of the data. That's why I'm setting this test site to 0.2. 0.2 basically means like I'm keeping 20% to test. I'm giving you 80%, right? So giving the model 80% of the features and their corresponding target, and I'm going to give it 20% to test. Right, that 20% is not going to have the target. So the model is going to predict what the target is, and then I'm going to take what the model predicts and compare it to the right answer, right? And see which one it got right, which one it got wrong, and all those kind of things. Okay, so that's what we're going to do here. So I'm going to define the independent variable as x. The dependent variable, I think I also forgot to mention that. So we also have what's called independent and dependent variables. So independent variables literally mean, this is a good example. So if I want to measure how well an athlete sleeps, right? And I have things like nutrition, I have things like exercise, I have things like number of Friday night hangouts. Okay, so Friday night hangout is independent of nutrition. It's also independent of what did I mention? Exercise. Okay, so Friday night, exercise, hangout. Three of them are like independent of each other. But the thing that is dependent on the three of them is the amount of sleep the person gets. So if you have poor nutrition, you probably sleep poor. If you do too much hangout on Friday, definitely you're not going to have good sleep, right? If you don't exercise well, there's a possibility that you don't sleep well, right? So the sleep is depending on these three values, but these three values are just like on their own. So that's the idea of dependent and independent. So the features itself, like independent, then the target is depending on all these features, right? So that's the idea. Okay. And they also refer to as endogenous and exogenous. Exogenous independent, endogenous dependent. Okay. Great. So Now to do that split, we're going to do like train test splits, import sklearn, scikit-learn. So scikit-learn is a library that provides these cool functions. I mean, you can probably write a Python function to split it, but I mean, just one line, you can do that. So it splits it into the train, so the subset of the train, subset of the test, subset of the targets for training, subset of the targets for testing, right? So now, I want to build from scratch. So the first thing is that, let me see, if I'm going to switch my tab, sorry, let me just stop sharing here and then start sharing here. So, Teams is hanging. Hey, funny because I actually practiced with this and it seemed to work well. And now it just doesn't want to work well again. Okay. Uh, uh, okay. Um, I think you all can see this this. Oh, great. Okay, cool. Okay, it seems like it's a few seconds lacking. Yeah, right. So now remember that our equation is y, sorry, is y equals to what? M x plus c. Okay. Now and we said that this c is a what? Is a bias. Okay. So now the first thing we want to do is we want to define this c. So we want to define the c for the training set. We also want to define the c for the test set. That is the one I'm keeping behind, right? Why do we need to define for the test set? You soon see. Okay. So now what we want to do is that by default, we want to set this c to equal to 1. And so that's why we're creating a list of ones that have the same shape as our training set and a list of ones that have the same shape as our testing set. And we are combining together. So we are now adding this list of ones to our training set. We're adding this list of ones to our test sets. Okay. So it's like you have set of ones, ones up to like maybe you have to n, okay, plus the original train set, that's x train. Sorry that my handwriting is horrible. Sorry. Okay, so that's like that's the idea of what we want to do. So let me stop sharing here because if I don't, it's gonna okay, it's cool. So I suppose you can see my new screen now. Yeah, yeah. Cool. Cool. Okay, great. So that's like what we're trying to do here. Okay. Yeah. So now after we've like defined that C, the next thing we want to do is to build the actual model. That is the W times X plus C for all the X's. And here we have just 2X. Okay. So, and that's why we're having like a math mole of X0 of T, right? So now what this does really, just like a lot of linear algebra, blah blah blah, takes the inverse, takes the transpose, and let me go back to the equation. So that, yeah, and this is what that line of code is trying to do, right? Okay, trying to see if I can like beat time and perhaps go to linear models for classification. So now when we sort of build that, we're going to get a theta. So now from this theta, we can extract two things. We can extract the intersect, right? And no, sorry, from that theta, we can extract the parameters, right? That is the actual value of the theta. And then we have the intersect. Remember the intersect, the x equals to 1. So when you print the theta, remember that, right, this is the theta, right? The theta for the intersect, the C or the W naught, right? And then for the other two features, the height and the weight. So now I'm putting this in the data frame, and then you can see it here. You can see theta 0, which is for the intersect, is this. Theta 1, which is for the height, is this. Theta 2, which is for the weight, is this. So this is like just a simple linear regression model built without any scikit-learn library or something. So now we can compare this with actually calling the linear regression model from scikit-learn. So to do that, I mean, you don't need to write all those complex stuff. You just define like whole linear regression. You fit it. Fit means train, right? So here we don't need to specify that, oh, x underscore 0, which is or your intercept is equal to 1. It does that, it sort of sorts that out by itself. So yeah, then the next thing we do is now we want to extract the theta itself from this train model. So here just defines model and train it. Yeah, I think I ran out of out of time. But yeah, so just defines the model, trains it, and done. Super fast. Then we want to compare, so we extract the theta, and then we add it to our already defined table here. So now you have like theta 0, the intersect is the same for the both of them. And then you see that our theta that we calculated by ourselves and the theta that we calculated from calling sklearn linear regression is the same thing. The same goes for the height, the same goes for the weight. So what does that tell you? If you want to show off, right, that you know this stuff, you can just like do it by yourself, and then you look like a guru. Okay, so now we've built the model. I want to see how well like it performs. So we can decide to predict this thing by ourselves, right? By just getting the math model of the x test that we've added the intercept to, right? So this is why we need to do that, because our theta has 3 values and our original x test has just 2. So it has like theta has 3 dimensions, x test has 2 dimensions. You cannot like take you can multiply that. So they have to have like equal number of dimensions. Okay. So that's why we needed to add that extra value to x test at the beginning. So doing that, we get the prediction, and then we can calculate the mean squared error from that, and then get the error. So the mean squared and the error squared. So these are like these are two metrics we can actually use to see how well our model is performing. Okay, so the mean squared error is 1.7, R squared is 0.98. The lesser the better, always. Okay. Yeah, no, just forget that. So I try to do the same thing for the That one was the one that we did ourselves. So this one is with calling the linear regression model itself. So you just call dot predict, and then it predicts the value for you. And then you just call mean squared error directly from sklearn, and then it calculates that for you. And it can also like get the score, and then calculate that for you, like super easy, right? Okay, so let me see. Are there any questions? Any questions right now? That's like how to build the linear model from scratch. Let me check the chat. Okay. Sorry, Windows users. Someone is asking if there's a difference between ML engineer and ML scientist. ML scientists, I've never heard of ML scientists before, but I think you probably mean data scientists. So data scientists do ML. The only thing an ML engineer does is that you know data science, and you also know the engineering part, which is like the deployment part, how this thing works in production. So you know data science and you know software engineering very well. That's like an ML engineer. An ML scientist, or what you mean as a data scientist, knows more of that data science itself, right? Okay, you asked me to share this. I shared so in the slide I shared, here, yeah, actually access to scan this code. So if you scan this code, you're going to get access to this. But let me just share it in the chat so that everyone can just, okay. Yeah, so I sent it to the chat. ML, oh, you found the ML scientist. Maybe just PR, but really it's data science. The only thing I know that's different is having research scientists. So research scientists are like on a whole lot different level. So you have research scientists, you have research engineers. And research scientists are higher than research engineers in terms of pay and all those sort of things. So, yeah. And the difference is that research scientists need a PhD, but research engineers do not need, probably just an MSc is okay. That's research. Yeah. So ML scientists, probably just PR, but it's the same thing as a data scientist, really. Okay. So I'm not going to go in depth for linear models of classification because we're already out of time. But what I'm going to do is I'm just going to explain the idea behind it. So, like I explained for regression, right? You have the goal in regression is given a set of features, you have your targets, right? Now, and these targets can be like anything, like I said, body mass index, it can be 0, it can be 1, it can be 10. But then in classification, you have like specific groups already, right? So you can say that given an input vector X, you want to assign it to one of K discrete classes, right? Where K equals to the number of classes you have, right? And I'm describing the classes as CK, okay? So now you can only assign one of the X, which I can say XI. You can assign XI to only one class for each I in X. Now I feel like I'm a math teacher, but literally that's like the mathematical representation of all that. What it's just saying is that every row in your data set can have just one class. So for every row in your data set, you have a corresponding class. That's what it's saying. Okay. So in regression, your target T was a vector of real numbers, right? But here in classification, your target T represents class labels. Okay. And then if it's a binary representation, you have your class is either 0 or 1. So it's either true or false. It's either cat or dog. It's either 1 or 1, like this or the other, right? And one of the advantages of this is that we can predict the probability of getting this class or the other class. Yeah, really cool. Yeah. So I'm supposed about like probability already. Yes, I love probability. So the idea is this. If I'm saying, or the model is saying, if I say, okay, this is a picture, I know it's a picture of a cat. I'm saying the model, what is this? So I want to know how the model decides that this is a cat. What is the probability that the model assumes that this is a cat or this is a dog? So that probability, or what they call level of confidence, can allow me to measure how accurate it is. So if the model says, okay, with the probability of 0.8, I think this is a cat, okay, yeah, the model is very confident. If the model says, with the probability of 0.4, I think this is a cat, then now decides, okay, my confidence is 0.4. Should I make it a cat or a dog? If my confidence for the cat is 0.4, then it means confidence for the dog is 0.6. So which of these would likely be the label? It's probably a dog because it has a higher confidence for that. So this is like behind the scene of how it actually says, oh, this one is cat, oh, this one is dog. Okay, so now the fundamental idea is sort of building what they call a discriminant algorithm or a discriminant function, right? And what it just does, discriminate, not the bad discriminate, but then just like take an input vector, assign it one of k classes. Okay, so similar to the linear, it's just like the same linear model for the two. The only difference is that is the result, like the input value the same, the output is what is different, right? And I think here I explained W parameter, or you call it the weight vector, and W naught is the bias. Okay, so and we can call the negative of the bias as the threshold. That is what is threshold. So if I say, oh, something is greater, if I say, okay, this is the middle point, if it is greater than 0.5, give it this class. If it is less than, give it the other class. That's for a binary scenario. Now, suppose we have a case where we have greater than 2 classes, right? We have more than 2 classes. Now, some underlying ideas or algorithms that have existed is where we have one versus the rest, where we introduce k minus 1 number of classifiers. So you have this linear binary classifiers for each k minus 1, right? And use it to solve that problem. That's like one versus the rest. So it's either, so if I imagine I have like I have cat, dog, rats, and I want to use this one versus rest. So I build a model to distinguish. So it's either cats or the rest. So I have 2 classes. I have cat or the rest, cat or others. I think that's the better, cat or others. Then I build for the other one, dog or others. The other one, mouse or others. So that's one versus rest. Then the other is one versus one, where it seems like a little, where you have k into brackets k minus 1 divided by 2, number of binary discriminant functions, where you have like cat or dog or mouse, cat or mouse, right? So instead of the others, it's one versus one. So these are like some existing intuition in how you can actually go about it. But we're going to use logistic regression like for binary. Okay, and we're going to try to find the relationship between features and the probability. So now, the process of saying, in neural networks, the process of saying, oh, if it's 0.5, give it this class, or give it this class, right? We call that like a sigmoid function, right? Converting the probabilities into classes. And this is when we have like more than binary, right? So we have more than 2 classes, we have so many other classes. You can use a sigmoid function to do that. So there are also like different types or classes of logistic regression: binary, multinomial, ordinal. You can like read up that on your own. So yeah, I'm going to stop here for today because we're way ahead of time, and I'm going to I'm going to send everyone again like an email of all these resources so you can like go over them yourself, and also like these blogs. And also I'm going to share with you like some Microsoft Learn courses. They're free, you don't have to pay for them, where you can like learn more about machine learning. And I assure you, you're not going to see any maths. So no fear. So yeah, thank you so much for coming to this presentation. I also didn't hear any more questions. Okay. Okay, someone is asking me to explain data scientist versus data engineer. A data scientist is more focused on building models, cleaning the data, uh, engineering features, doing all those. Sometimes it's like really, it sounds so simple, yeah, but oh my God. Oh my God. It's a lot of work, especially in real life. I mean, the data set we use is just height, weight, BMI. Oh, but in real life, you have like a mess of data. So that's what a data scientist does. His work is more around taking data, cleaning it, pre-processing, storing, um, and building models, evaluating, testing in real life. A data engineer is more about how the data scientist can even use this data. So let me give you an instance. For example, you're working with clients and you maybe want to build models for clients. Clients have like where they store their data. So for example, some use Google Analytics, some use SQL, some use so you have like so many data sources. How can you, a client can even have like 5 different data sources. So how can you unify these data sources and create like a pipeline, an inflow, right? Such that the data sources come in a format that you want or that is needed for the data scientist. You don't want to make the data scientist work even harder, right? That's what the data engineer does. So more about getting this data ready, available for the data scientist to use. And trust me, it's a whole lot of work, especially when you're dealing with big data, right? And you're looking at speed, latency, availability. Yeah, that's why it's a role on its own. It's so much more than a single data scientist should do. Okay, are there any more questions? You can like raise your hand if you have like a question. Okay. Okay, great. So if there are no more questions, thank you everyone for staying, not running away because of the math. And I hope that you actually found it very insightful. Um, I'm going to send everyone an email for those who registered, and you're going to get the resources. So have a wonderful evening and bye.